Ladies and gentlemen, please welcome to the Networking Plaza stage Peter Stonard from NXP. He'll be speaking about secure connections for a smarter world.
Thank you very much. Welcome everyone. NXP is a semiconductor company. We make the chips that go on the boards that use many of the equipment that you see here. But today I'd like to introduce you to an enhancement to something that you may already have in your pocket. So a quick couple of questions, if I may. Do you have a mobile phone? Show of hands. Yeah, I thought so. Most people have a mobile phone. So the question is, do you have a smartphone? Sure, this is the kind of phone that does data as well as voice. Very good. So now the really cincher question, does your smartphone have NFC or near field communication capability? Chances are next year many more people will have that feature, and it's relatively new into the marketplace. So I thought I'd run through some of the things that you can do with it, why it's important, why it's an emerging technology. If you're not familiar with smartphones, you have kids in the house, there's a great quote here from Buzz Aldrin. Kids, help your parents if they don't know how to use a smartphone. And that sort of sums up how modern technology is. It's moving very fast, and if you want to be part of it, you need to grab the coattails and come along with us. So you'll find NFC technology in all the major brands of phone, regardless of which brand or model you have. More than likely it has NFC built into it. So what exactly is near-field communications? It enables your smartphone to communicate by briefly touching or being in proximity with another phone that has NFC enabled. There are no wires, there's nothing that physically transfers. There is a magnetic resonance coupling between the two phones. And that's how the transmission is made from one phone to another. The carrier frequency is in an ISM band, which is unlicensed and available globally. So the way it works is the transmitter operating at 13.56 megahertz can transmit data somewhere in the range of 100 kilobits per second to 400 kilobits per second. To make sure that all of the phone brands and all the phone models are interchangeable, there is a NFC forum which was founded in 2004 by a partnership between Nokia, Philips Semiconductor, which later became called NXP, and Sony Corporation. Now, NFC is not the same as QR. You may have used the QR codes. Your phone may have a QR reader on it, which uses the camera. So the important difference is, with QR codes, you can only read the code. With NFC, your phone, depending on its capabilities and permissions of the NFC tag, you can write data and store data on the NFC tag. So it's an interactive rather than a read-only function compared with QR. So there are three modes that NFC can work in, and these are generally available on all smartphones that have NFC enabled. The first one is called NFC card emulation. What happens here is your phone works the same way as an NFC card that you may have in your pocket for some kinds of transactions or for paying for services if you use, for example, public transportation. The second mode is where the NFC is both a reader and a writer device, and your smartphone can change the data that is stored in the NFC tag. And this might be helpful to you if you have a tag on something that you have to update periodically, and it might be useful in a business situation where you want to prove that someone took an action. They can approach an NFC tag with their phone and record that they were there. This might be useful for, say, a roving security person who has to make the rounds at a certain time during the night. The third thing is peer-to-peer communications. What this means is if you have an NFC-enabled phone and someone else also has an NFC-enabled phone, the two of you can exchange data by bringing the phones into close proximity. Now, at least one phone vendor has advertised this as a quick touch, where you briefly actually encounter another phone with similar technology. And it's like exchanging a business card. It's done electronically and it's much faster. And you have more detail because you have a better depth of information that can be stored in the NFC realm compared with the business card. So what typical applications are used for NFC? The most popular one is money transactions, purchasing goods or services that require authentication and security. So NFC has to have those features so that you have confidence in putting money on your phone and using that money in transactions. And if you're the retailer or service provider, you want to make sure that you're receiving the money and you're not somehow spoiling the transaction. So the most popular by quantity of applications is commuter tickets for trains, buses, and other public transportation. This started with a company called Micron Fair in 1994, and that company was later purchased by Philips and also became part of NXP. Now here's an amazing statistic. The number of tickets that have been used with this type of technology is 10 billion. That's 10 million bus or train rides since 1994. And what is an even more amazing statistic is that we have delivered 150 million readers. So there must be multiple readers in all train stations throughout the world for this system to be readily accepted and useful. In retail transactions, we have two new players on the playing field. In 2011, Google partnered with MasterCard, MasterCharge, and they introduced Google Wallet. Last year, Apple joined in with something called Apple Pay. So how does this affect the user experience? NFC does not require a cable connection or any physical transfer. It just requires proximity between two devices. One of them becomes the transmitter and the other one becomes a reader. An example would be if you are making an in-store purchase at a coffee shop, for example, you might be using your phone as the sender, and the coffee shop may have a reader on the counter that you come into contact with to make a transaction. Now something that's interesting about the technology is alignment of your phone and the reader is not very critical. But it does vary, and that's going to be something we'll address in the next part of my presentation. It's important for the user's experience that when they bring their phone close to the reader, they don't have to fuss with it or scratch their head and wonder whether the transaction really took place or not. The main thing that changes the ability of the reader and the phone to work well together is the field strength of the signal that's coming from the phone. And the field strength can vary for a number of different reasons. The most obvious one is the state of charge of the battery that is in the phone. If you charge your phone overnight and you take it with you in the morning, and you start using it for your morning coffee, you may have very good performance from NFC because the field strength is strongest. Towards the end of the day, when you're buying that snack to go home, you may have less success with your NFC experience because the phone is not as strong as it was in the morning, and it's now difficult to get a reliable first-hit reading when you bring it near to the reader. The second thing is the orientation of the antenna. There is a coil in the body of your phone that has to come into alignment with a similar coil that is in the reader wherever you're making the transaction. If you're clumsy with the phone, you're in a hurry of carrying packages, you may not carry the phone in the right orientation to reach out and make the first hit with the reader. This problem is reduced if your transmitter is producing a stronger signal. It is therefore less fussy to orientation, and the user will notice this right away. They will realize that their phone is now making reliable communication, and they start to have confidence in the system, and they use NFC and online payments more often. The next problem is the size of the antenna. Although there's a trend recently to make phones bigger because we want a larger viewing screen, more stuff inside the phone, and in doing so, the antenna space has been compromised. For example, in the Samsung product, they hid the receiving and transmitting coil for NFC underneath the foil wrapper of the battery that's in the phone. Some of you may have seen this on internet rumors or in popular press. Users of this particular product were very suspicious that there was some kind of secret transmitter built into the battery that was in their phone. That's simply not the case. It was just convenient for that manufacturer to put the coil inside the foil of the battery. So it may be necessary to make the coil itself smaller, either because we're trying to get a smaller footprint in the phone, or because we have other stuff we want to put in the phone and we have to move things around. So one way to overcome that problem is to increase the strength of the signal and therefore make the coil itself just a little bit smaller to meet ergonomic and style requirements. Did you realize that your smartphone is really a radio? In fact, it's a multiple radio. The typical modern smartphone has 5 radio systems all running at the same time. And this is a challenge for handset designers to make these radios isolated from each other so they're not interfering. So let's do a quick rundown. If your phone can send and receive voice phone calls, then you have cellular phone service, which is also used for SMS or text messaging. Currently, there are 10 different radio frequency bands available throughout the world. They're not all available in the same place, but it does mean that your phone has to be frequency agile and modulation agile to operate on those different systems. For example, in the long-term evolution cellular band plan, there are radios that operate from as low as 700 megahertz to as high as 2600 or 2.6 gigahertz. The second thing is Bluetooth and Bluetooth low energy. This is both the transmitter and the receiver, and it operates on a specific band of frequencies centered around 2.4 gigahertz. And that's 2 radios in the handset. The next one is Wi-Fi. If your handset is capable of connecting to the internet, you have Wi-Fi service and then another set of radios. And these operate at 2.4 gigahertz or 5 gigahertz. The next one is a receiver only. It's for GPS. It receives the signal from the satellite that allows your navigation and location services to work on the phone. Although it's receive only, it's receiving a very weak signal that is coming from a constellation of satellites, and any interference that's produced by the phone itself will make it more difficult to receive that GPS signal and will make the service less reliable. So it's necessary to isolate each of these radio and transmitter sections in the phone. The last one, which is today's topic, is near-field communications, which is both a transmitter and a receiver. It operates at a much lower frequency than any of the others. It is assigned to an ISM band, which is unlicensed communication, at 13.56 megahertz. By the way, if you had an older phone that had the antenna that pulled out, that antenna needed to be approximately 4 inches long to be effective. If you replaced it with a flip phone or a phone that had the antenna built in, and most smartphones are built this way now, the antenna is smaller because it operates at a higher frequency. It only requires a 2-inch antenna. If we were to use an antenna for near-field communications, it would be approximately 60 feet long, because the band is at only 13 megahertz. So what's really happening is we're making a magnetic field rather than electromagnetic field as we have with a radio signal. So there's some differences required for NFC to work compared to the other radios. But the important message from this slide is there are many radios in the handset, and these radios have to be isolated from each other for each one to do its job effectively. Now here's an interesting graph. This is what has happened to cell phones over the life of their introduction, approximately 30 years. As time has gone by, our phones have become more awesome. They have new features, they have better ways of operating, and they offer more services to the user. In doing so, our phones have become antenna ability or effectiveness has decreased by as much as 75% over the last 30 years because phones have either no visible antenna, a much smaller antenna, or the antenna is crowded in the radio space by the other signals that are necessary to run on the radios. Plus, some of the antennas are used for multiple services, so there's a compromise in their electrical performance. And all of this goes into making a more desirable, more user-friendly experience in cell phones. So how can we boost this problem into something better? NXP has an answer for you. It is very simple. We have a specially designed DC to DC boost converter that takes the battery voltage, regardless of the battery state, and boosts it to a higher voltage. By operating the NFC system from a higher voltage that is constant regardless of the state of charge of your battery, we end up with a stronger, more reliable and consistent radio signal throughout the working life of the phone before it needs to be recharged. The circuit itself is very simple. It is an integrated circuit which NXP makes, plus a few external components. In fact, we only need 2 capacitors and an inductor to complete the design. So the advantages are a consistent RF signal. It has the same signal strength regardless of the battery charge state. It's a stronger RF signal because the transmitter is operating from a larger voltage. I'll show a graph in a moment that compares the transmitter voltage to that of the battery over the life of the battery charge. It improves the user's experience because now they have better trust in their phone working in NFC. They don't have to fuss so much with orienting their phone to the reader, and they have a better trust in the technology, so they'll start using it more. So it becomes a useful and in-demand feature for cell phone handset manufacturers. So here's the graph I just mentioned to you. The red line is the battery voltage, the charge of the battery as it is depleted during the day. When your phone is at home on the charger or wherever you choose to charge your phone, the battery voltage could be a little bit north of 4 volts, typically 4.3 volts. At the end of the day, when your battery indicator is saying time to charge the battery, it's almost dead, the battery voltage is only 2.3 volts. It has slowly declined over the day. The user typically doesn't notice this, but if the NFC subsystem was connected directly to the battery, it would have an immediate consequence because the strength of the RF signal would decline over time. So what we do with our DC to DC boost converter is take the battery voltage and we boost it to a higher voltage and we regulate it. And that higher voltage is typically 4.75 volts. It's actually higher than the battery voltage itself, which means that we have a stronger signal. It also means that the signal remains consistent over the charge of the battery, and this all leads to a better user experience. So what's the pieces that go into making the NFC system inside the phone? The first one is the antenna. It's really the coil of a transformer which works together with the coil of the reader when you bring the phones together or you bring the phones close to a reader, a cellular reader. And the larger you can make that coil, the more turns you can have on that coil, the stronger the signal will be. But you're fighting against personal choice. You want to make the phone small and compact. You've got other things in the phone that have priority, so we end up making the coil small. So there are some disadvantages to having a compromised coil or transformer winding for the phone antenna. And these are very noticeable to the user. They affect the user experience. The first one is compromising on the size of the case or the shape of the phone. The second one is not so obvious. Depending how you hold your phone may depend how effective it is in coupling to the reader. If you've been in an airport recently and you've had someone in front of you use their phone as a pass to get on the plane, you know that sometimes that technology does not work. By the way, it's not near-field communication. It's optical. It's reading from the screen of the camera. But if the person holding the phone has a screensaver that kicks in, they have to reset it. If they fumble the phone, it doesn't line up with the camera that's in the pedestal, they may have to do it more than once to get through the gate. So the user is very aware of limits of this technology, and the DC to DC boost converter alleviates many of the problems with NFC. We think it's a technology that is definitely going to take off and be popular in the future. So what do we need to do to add this DC to DC converter to our phone? The chip itself is very tiny. As I mentioned earlier, it needs external components, an inductor, two capacitors. Our DC to DC converter operates at a higher switching frequency, which means that those external components can be made smaller. Space is everything inside a handset, so having a smaller footprint in the body of the phone is highly desirable. So we can package those three components plus our chip inside a space that is approximately 12 square millimeter, which doesn't sound like very much, but in the phone world is very expensive real estate, so we want to conserve it and use the least amount possible. The next issue is because our part is a switching converter and it uses an RF signal to do the switching at 3.0 megahertz, there's a possibility that any leakage RF energy from our circuit can interfere with other radios. And we already know from the previous slide that there could be 4 other radios plus the NFC circuit operating at the same time. So one of the things we've done is make sure that our switcher is friendly in the neighborhood when it's inside the phone, and it doesn't produce interference that could affect other phones. Most of the other phones have hexagonal circuits that down-convert the incoming RF signal to an area where it can be automatically decoded by a software-defined radio, which is basically a radio that's implemented in a microcontroller or system-on-a-chip that is inside the baseband of the cell phone. So what we've been very careful to do is make sure there's no energy in a very important band that runs approximately 10 kilohertz to 1.5 megahertz. Any energy that's there can easily get into another component in the phone, but although an effort is made to shield the parts and locate them as far away as possible, it's very difficult to block the low-frequency RF signal once it's generated. So we made a point to reduce those spurs as much as possible so that they are not a source of interference. So in summary, DC to DC boost converter can benefit NFC applications by providing a consistent 5 volt or 5.25 volt output independent of the state of charge of the battery. Secondly, the boost converter family has proven performance advantages when coupled with the NFC chips produced by NXP. We have tested this on all the major card types, so we know that it will work well with the most popular systems that are in the field. So the advantages of the NFC DC to DC boost converter family are one that uses high switching frequency at 3.0 megs to produce smaller external components. Secondly, it has lower baseband noise, which could interfere with other radio parts of the phone. Anyone have any questions for me? If you would like to contact me afterwards, or if you would like to contact me after the show is closed, or if you would like to send a question, if I can't answer it, I will find an expert somewhere that will answer it for you.